2.4, rates of change, tangent lines, and sensitivity. So in this class, we won't be focusing on sensitivity. That's why I crossed it out. So in section 2.4, we will only be dealing with the rate of change and tangent lines. Okay, so a quick refresher. What's the rate of change? What's a tangent line? Remember that the average rate of change, nothing but a slope, so y2 minus y1 over x2 minus x1. But tangent line. What is a tangent line? Quick refresher from your previous math classes. Some of you guys might be thinking of a tangent line that looks something like this. You are correct. Okay, so a tangent line is perpendicular to the radius of a circle, and it touches that circle at specifically one point. Okay, so what we're going to do is in this course, in calculus, the limit process, what we've been dealing in the previous sections, the limit process is very useful to help us determine the tangent line of any function, okay, at a specific point. So not just circles. So in this case, we have this function, okay, y equals f of x, okay, and I drew a secant line. So again, quick refresher. Here we have a tangent line. This is a secant line. Okay, so before I can show you how we use the limit process to find the tangent line of any function at a given point, we start with a secant line. Okay, so in this secant line that cuts through the function y equals f of x, we have a point. I'm going to call this x value a, therefore the y value is f of a. So we have point P that's at a comma f of a. Okay? Now, what I'm going to do is I'm going to go ahead and write this x value for the second point that cuts through that belongs to the secant line. This second point, I'm going to write it in terms of a. So it's going to be a plus something. Okay, and that something is this. So a plus that. So what I'm going to call that, let me go ahead and label that as h. Okay, so a, and then this gap here, we call it h. This x value is going to be a plus h. Okay, so that value is a plus h, and that means the y value is f of a plus h. Okay, and if we label this point, let's say q, this point here is a plus h, comma, f of a plus h. Okay, so here we have points P and Q that belong to this secant line, this blue secant line. Okay, but I said that in this class we will be able to find the slope of a tangent line at any x value for any graph, for any function. Okay, so right now I don't have a tangent line. Okay, I don't have the slope of a tangent line, let alone the tangent line. So let's start off with this secant. Let's start off with the slope of this secant line. Okay, so I'm going to plug in these values that we just found into the slope formula. Okay, so y2, which is f of a plus h minus a. A oops, over this a plus h minus and we'll do a. Okay, so here's the slope of the secant. Slope of the secant line is this, which is just f of a plus h minus f of a over, well, those cancel out. We just have h here. Okay, but this is the formula for the slope of a secant line. Okay, we want the slope for a tangent line at a given x value. Okay, so what if we want it at this given x value, x equals a? Okay, we want it at this point. So let's pretend we can actually move this point here. Okay, let's pretend we can move it and get it real close to this point, x equals a. So if we can move it, it'll eventually, look something like this. Okay, as we move it closer and closer and closer. Okay, as we move this point closer and closer and closer to x equals a. Okay, so this blue line has to move along with it. That's not what I want to do. So okay, so here eventually we're going to get close enough where this point will get real close to that point x equals a and f of a, so point P. Okay, so what's happening to h as we're doing this? Well, the closer we get to point P, h is getting more and more insignificant. Okay, it's like it's becoming zero. It's going away because eventually it's going to be point Q will eventually be a plus 0, where h is 0, comma, f of a plus 0, which is just a comma f of a. Okay? So, in other words, if h is going to 0, if h becomes 0, then this point Q will become point P. So what I'm saying is that the slope of the tangent line is equal to this same thing, f of a plus h minus f of a, over h. However, it's the limit as h approaches 0. Okay? Okay, so what I'm going to show you guys right now, hopefully is a little animation that will help you see this. And I'm going to use GeoGebra. Okay, so here we have this function, this blue function, and we have this gray secant line. This red point is a, comma, f of a, and this blue point is a plus h, comma, f of a plus h. Okay, so according to this function, okay, we don't know what, oh, here's the exact function, negative 1/2 x cubed plus x squared plus 2x minus 1. Okay, that's the function. H in this particular case is 1.3. Okay, so pay attention to h. H is 1.3, actually 1.38. Okay, now, and also pay attention to what happens to the line, to this gray secant line, as I move this cursor so that h gets closer and closer to 0. See, it went from what it was to 1.02. Okay, now I have it at 1.5. Look at what happened. Look at what happened to the line. As h gets closer and closer and closer to 0, it'll eventually become the tangent line. Okay, one more time. Okay, so that's what I'm trying to explain here. Okay, except I don't have all those animations, but that's exactly what I'm trying to explain here. So this is going to be very, very important. So go ahead and write this down. The slope of the tangent line of f of x at the point x comma f of x is, well, that's just what we found out, the limit as h approaches 0 of the function f of a plus h minus f of a over h. Okay, and in part 2, I will show you an example of how we apply this. Okay, that's it for this video.